Good day everyone. Today I am going to present my final year project 2. The title is Hardware Implementation of CNN Handwritten Disease Recognition. My name is Deezer and Alexander, measure number CE210079. This is the result for ARM Cortex-A9 implementation using C++ programming. The time taken is 59 seconds for the 10,000 image detection. This is using OpenGL hardware implementation. The time taken for 10,000 image detection is 8 seconds. So let's go for the Verilog design 1. So Verilog design 1 is primarily for speed, and because of that the logic is more. Okay, this is the top level design block diagram for Verilog design 1. So get image, this is the input for the image. It's a kernel filter, so until kernel 0 until kernel 31. It's a block diagram for the kernel. It's a fully connected layer. The block diagram for the fully connected layer. Okay, let's see the top design for the Verilog design 1. So consists of the get image. That is the input image for the ROM. The input image for the ROM we store here, and the address generator for the image. Okay, for the kernel 0. So kernel 0 is the image in on the get image, and it's multiplied with the weights for the filter 0, 5 by 5 filter. Okay, next. Okay, after the multiplication is accumulate. So after the final accumulation, the output is the rec bias. After add with the bias for the filter 0. So after the filter 0 is the ReLU function, where all the negative value will become 0 and the positive value remain. So this address value is for the assigned address value is for address select, address 3 and 2. Press 1 for storing the ReLU feature in the RAM, 1 for max pooling address generator. This is the max pooling function. So let's see the output image in the room, and this is the RAM 0 of the ReLU output. So after the ReLU output will be the max pooling. So after the max pooling layer, we still will multiply with the fully connected weights, and it's accumulate for the digit 0, 1 until 9. This is for filter 0. The output digit 0 until 9 is for the filter 0. As you can see in the top layer, digit 0, filter 0 until filter 31, and it's added with the bias. So same goes until digit 9, 0 until 9. So the summation of the digit 0 until 9 will be go into the sort module. So this where goes. Okay, this is the sort module. So module is the consists of the summation of the digit 0 until 9, and the output is the digit. Okay, you can see we can so this is where we will get the digit. So when we select, so we will know the value of the digit 0 or until 9, which one is the larger will indicate the recognition of the digit. So at the same time we will detect which digit it recognizes at the sort module. Okay, let's see the output waveform. Okay. So as you can see in the design 1, so all the digit 0 output until digit 9 we're getting at the same time. So the largest value will be the digit 7, because the input image is digit 7. So the output is will show as the digit 7 after comparison in the sort module. So as you can see, in the Verilog design 2, where the multiply is less and the logic also less, so its comparison the speed will be lesser than the Verilog design 1. This is the top module design block diagram. It's the same as before. Get image, the address generator is the kernel. So inside the kernel, we have only one multiplier for the input weight. Previously, we have two multiplier. So this is a fully connected weight. It's a block diagram for fully connected weight. Whereas the accumulator, only one multiplier used. So the accumulator we will get the output of the accumulator depending on the digit address and digit W address generator. Let's see that I just mentioned about. So in the Verilog design 2, it will be kernel 0 until kernel 31, then the address generator for the weights for fully connected layer, and this is the fully connected layer modules 0 until 31. So output of the each fully connected layer after the multiplication and the summation, so will be add together digit 0 until digit 9 and add with the bias. Later on we will compare in the sorting module, and before I previously mentioned, just same concept. So let's see what's the difference in the kernel previously and now. Okay, as you can see, previously this completion process will having a two multiplier, whereas one, the accumulator equal to the image in times with the S weight, and secondly the accumulator equal with the image in times with the S weight plus with the accumulator. Okay, and here we having a 2 RAM for the ReLU and the max output. So this is the address generator for save in the ReLU RAM, and this is the address generator for read from the ReLU RAM. Okay, so after the output from the ReLU RAM will be having a max pooling. Okay, the max pooling will be stored in the RAM max 0, and this is the address generator for store in the max pooling, and this is the address generator to get to read the data from the max pooling. Okay, okay, this is the input image from the ROM. This is the feature, the ReLU output stored in the RAM. This is the max pooling output stored in the RAM. Okay, now as we can see, we're using the design 2 using one multiplier and one accumulator. So after the done of the digit 0 summation and the multiplication with the fully connected weight, then only digit 1 will continue with the digit 1, then digit 2 until digit 9. So previously we can compare the waveform from the previous two design. This where the summation of the digit and plus with the bias 0 until 9 at the same time, and we getting the output is the digit 7 as the input image is 7. So as here, this in the different clock cycle, where after the done of the digit 9, then we having the start for the sort process, then only you will getting the output for digit 7. We see the output waveform. So this is the performance comparison between the CPU and the using C++ programming and the FPGA OpenCL and using the design 1 and design 2. So the operating frequency is at 925 MHz for the CPU, and the rest for the FPGA is 50 MHz. For the execution time is 0.056 second for one detection, and for the FPGA OpenCL it's a 0.0008 second, and for the design 1 it's a 0.004. It's much more faster than the design 2. Gen 2 is reduce time 0.0045. So the total of the logic for the OpenCL is quite large. It's 30650. For the design one, it's larger than the silent V, so we can't get the total register or the total memory bit. Need to use the larger FPGA to see. And for the design 2, which is a less logic compared to the all the logic utilization, is 9150. The total register is 17398. The recognition for the feature work. So an optimized hardware architecture for the CNN digit recognition with custom model to achieve higher accuracy for digit recognition. That's all from me. Thank you.